we'll take our look at the calendar. Yeah, the calendar looks good. Not too many more looks at the calendar. Okay, so we have spent the last 3 classes talking about math in nature. First day was about bees and the Fibonacci sequence, that list of numbers. The second day was about population growth, populations of greenfield at certain moments in time. We talked about linear growth and we talked about exponential growth, 2 different ways a population can grow. And then last class we talked about fractals in nature and we looked at some pictures of like ferns and lightning and things like that appear fractal-ish in nature. The next 3 classes, our last 3 classes of new material, are about math and art. Today we talk about math and music. Next class we talk about math and drawing things in perspective. And then our last class of new stuff is on the math of symmetry and tiling. So 3 classes on art, and then we're done. May 10th is the last Tuesday, Thursday class of the semester. That will be our review day for test number 3, which is again an ordinary test, not a cumulative final exam, but it happens during final exam week. It's on May the 15th, which is 2 weeks from today. So 2 weeks from today, this class will be done. You'll be taking your 3rd exam, and that will be that. Maggie.
For the test number 3, we're allowed to wear notes, right?
Yes, same 1-page sheet of notes for test number 3. Yeah. Okay, again, technically the project is due this coming Thursday. I have relaxed that constraint from what I originally handed out on the syllabus. I will take the project up to and including the last day, that exam day for us. But again, the benefit of handing it in to me early is that you will have a chance to revise it if you want to improve your grade, okay? So if you want to revise, you got to get it to me by 1 week from today. If you give me a project by Tuesday of next week, I'll give it back to you by Thursday of next week. Then you can revise if you wish, all right? Questions on the calendar? Okay, and then one last thing while the calendar is here is that our test number 3 starts a little bit earlier than our class normally starts. Our testing window begins at 10:30. That is when our test is, okay? Not at 11, at 10:30. Okay, so let's come back here to page 21. We'll talk some about math and music. Oh, and I handed out a reading on perspective. It's a photocopied thing from a book by Bennett and Briggs. We had some handouts from them way back at the start of the semester. It's the same book. We're coming back, so read that as part of tonight's homework. You'll see it referenced in tonight's homework assignment. Becca.
Oh, well, I was going to ask for tester. You want videos how to do it?
I will. I hope that I have. Are they not there yet? Okay, I think that there are already videos for the sample problems for test number 3. I hope. Otherwise, there's more work for me to do. Yes, I will post them. Okay, so we'll go to number 1. It says we're going to revisit a problem. I think I actually skipped this problem. So for the first time, we're going to take a look at number 1. We'll go all the way back to Doug. Okay, so Earth's population was 6 billion, and we're going to assume it doubles every 45 years. So between 2000 and 2090, how many doublings will have occurred? 2 doublings, right? Because you can squeeze 2 45s into the 90 years that we have available. So if we're going to double 6 twice, what do we land on? If we double 6 twice, what do we land on? 24, yes? You said 2 doublings. So if you wanted to be really careful and write everything down, you could say in the year 2000, we had 6 billion. What's the next year where things were nice? In 2045, which is when it doubled the first time and gave us 12 billion. And then in 2090, 24 billion, okay? It doubles twice. Okay, if instead of saying 2090, I had said 2900, well, it turns out that is a nice doubling number. If you kept making this list, you would eventually land perfectly on 2900. but we get annoyed when we have to do like really long, lengthy lists like that, right? So let's think of a better way. Remember last class or a couple of classes ago, we talked about different growths, linear, exponential. For linear, you gain the same amount every time. For exponential, you multiply by the same amount every time. Which one is this? This is multiply. Every time something happens, what are we multiplying by? Multiplying by 2. So it feels like this is an exponential kind of thing. So it feels like we should be able to use one of our fancy exponential formulas instead of listing this chart over and over again. Okay, here in English was our exponential growth formula. It said that if you want to know how much stuff you have at some moment in time, population at some year n, you do your start number times the common ratio raised to the n. So we've seen this formula. Okay, so what's the starting population for this example? 6 billion, I'll just call it 6, times. What's the magic ratio, the magic multiplier? It's always times 2. Now we've got to put the number of years. If I'm waiting to 2900, how many years have passed? 900. We can't. Yeah. We can't do this. What we would be saying here is that we double 900 times. That's what 2 to the 900th is. But we're not doubling every year. We're doubling every 45 years. So can you guys, either with a calculator or by hand, can you tell me how many doublings do we have by the time we get to 2900? So what are we typing in? Number of doublings. How do I find how many doublings happen in 900 years? What do I type? 900 divide 45. You guys agree? Every 45 years is a double. So how many of those 45s can you fit into 900? You divide. Okay, Jocelyn? That's 20. 20 doublings. So I shouldn't be doing 2 to the 900, which is 900 doublings. What should I be doing? I should be 2 to the 20. I should do 2 to the 20. If I just make it 2 to the 20, I'll get the right answer. But I want a way to do that calculation sort of built into my formula. So do you guys buy that maybe up here I should be doing 900 over 45? That is 6 times 2 to the, what did we say 900 over 45 is? It's 20. That's the right answer. Start with 6, double 20 times. That's how we type it in. Okay, somebody with a calculator, what do we get there? I actually think I might know roughly what this is. So this is, so 2 to the 20, 10,000 million. I mean, it's like 6 million and change, right? Like 6.36, what is it? 629, 1456. Yeah, I said 6.3 million. That was a pretty good guess, wasn't it? I'm more impressed with myself than you guys are with me. It's okay. Okay, so that's not bad, right? The population will be 6 million in 900 years. We can handle that. What is this? Is this 6 million? This is 6 million billion. That 6 we put in was 6 billion. This is in billions. Let's see, trillion, quadrillion, quintillion, 6 quintillion. I guarantee you we cannot sustain 6 quintillion people on this planet. So hopefully something will change between now and 2900. I won't be around to see it, but the math predicts this population. Okay, so let's see if we can kind of bring things together and come up with some formula. Let's take a look down here at number 3. This 45 years is something called the doubling time. 45 years is how long it takes for the population to double. So if we've got a doubling time, we've got a formula down at the bottom here. This is number 3. New population equals initial population times 2 to the elapsed time over the doubling time. Let me remind you of what we just did, because what we just did is use this formula without knowing it. Our example was, what's the initial population? 6 billion times 2 to the, what was the elapsed time for us? Was 900 years. Over, what's the doubling time for this example? 45 years. That's what we typed in. So the formula, I'm hoping, is reasonable. Hoping it makes sense. Yes, if you know how long it takes the population to double, this is the formula to use. Okay, let's see if it's reasonable, because actually the Earth's population just passed a significant milestone. 7 billion. We just passed it. I don't remember when, but it happened this semester, didn't it? February sometime, maybe? I don't remember exactly. Okay, so we just passed 7 billion. How about we try using this formula to predict the population, not in 2020, but in 2012. Let's try it. So use that formula for the year 2012. Initial population, 6. 2 to the, what's the elapsed time if we're looking at 2012? It's 12 years. 12 years have passed since we started this experiment. Divided by, in this example, it's always 45. That's the doubling time for this estimate. Okay, so this, all right, 7.2 or 7.6. So let's make sure we type this in carefully. This is definitely a calculator example. So if I type this in, there's one thing you got to be careful about. 6 times 2 to the 12 over 45. Yeah, this is going to give me the wrong answer. Yeah, that's too much. Okay. That's right, because you and I know that 12/45 is the exponent because we wrote it up there, but the calculator can't see how we wrote it up there. So we have to tell it that is one thing up there. This should be the right answer. Okay, 7.2 billion. This predicts 7.2 billion right now. In reality, we just passed 7 billion. That's not too far off. Okay, so that's around 7.2 billion. Questions on the new formula? Okay, so let's come back down here now to number 5. I'm going to change gears completely, but we will come back to that formula, I promise. Let's go to 5 here. Who's our reader? Justin.
Quality of sound pitch, how high or low the sound is. A shorter string will produce a higher pitch.
Okay, let's pause there. We'll go to Zach. Oh, can you get your calculator or your guitar out? Thanks. Okay, so looking at the piano, there is a very good mathematical reason for the fact that the piano is shaped this way. It's not shaped this way because of design constraints or because we think that that's a particularly beautiful shape, although some people look at pianos and say, wow, I really like the way that looks as a piece of furniture. But why are the things really, really long over here? Because long strings give you low notes. So if you push one of those strings down at the bottom, you get the low notes, the kind of bass notes. And as you push notes higher up here to the right, you get the higher notes, the higher pitched notes. And what kind of strings make those notes? Shorter strings, which is why the piano is really long on the left-hand side and really short on the right-hand side. And the same kind of thing on the guitar. So Alex is going to help us out today. So Alex, could you just play for us like an open string? Doesn't matter which one. And then if you could play the same string, but put your finger on that top fret. Yeah. And then keep going down. What's happening to the length of the string? It's getting shorter. What's happening to the kinds of notes we're getting? They're getting higher, right? Thank you. So it's the same thing up here, right? Alex is making the length of the string shorter to get the higher notes. Happens on a piano, happens on lots of stringed instruments. Okay. All right, let's go to number 6. We'll go to Brittany. Okay, let's pause right there. Again, sound is vibrations of air molecules. That's what it is. So Alex, play a note for us again. So when we hear that note, you are hearing air molecules vibrating faster than they normally would. When you hear my voice, I am pushing faster vibrating air molecules towards your ear. So when Alex plays that note, the string is actually moving. And in fact, if you ever watched one of these strings move, what does it look like when you just pluck a guitar string? It is vibrating. What does it look like? Yeah, doesn't it look thick? Like if you, do you guys know, have you seen this before? Raise your hand if you have no idea what I'm talking about. Like if you just pluck a string, it will look much thicker than the string is. Why? Does it get thicker when you pluck it? No, what's happening? It's moving so fast that your eyes cannot pick up on the little movements. It's too quick for us to follow. So the number of times that that string moves down and up per second is called the frequency. And it turns out that that the frequencies are generally like in the hundreds, if not the thousands. So what that means is that if Alex plucks one string, maybe the string, all right, so let's imagine the string at rest is just this horizontal thing. And then Alex plucks it. And so he pulls the string up in the middle, which is very unnatural for the string. It doesn't want to be there. So what's it going to do? As soon as he lets it go, what's it going to do? It's going to try to get back to horizontal, right? But is it going to do it? Just start up here and then it'll just zip back to horizontal? No, it's going to overshoot because it's just overcompensating. It's up high. It's really angry that it's up high, and so it's going to try to get to the middle, but it's going to pass it, and it's going to end up like this. So it wants to be here. Alex pulls it up. It says, I do not like this position. This is uncomfortable. I am stretched. I'm going to try to get back to equilibrium, happy middle. But it goes too far. And then it says again, I don't like being way down here. I want to get back to the middle. So what's it going to do? It's going to shoot upwards, but it's going to pass the middle and turn into the first thing. And it's going to go back and forth between these two ups and downs a bunch, really quick. So quick that what you see is this sort of shaded in thing in between the two extremes. And the frequencies, again, are sometimes like often in the hundreds. And so Alex plays a note, and it goes, let's call this up and down, and that's one cycle. Up to down, back to up. That's one cycle. It will do that hundreds of times in a second. And there's no way for our mind to be able to see hundreds of those things happening every second. It is way too quick. And that's why this string looks like it's shaded in, it's thicker. Okay, let's keep going. Who are we at now? Iris? Okay, Johannes? Okay, let's pause right there. So, can you play an open string for us? And then what I'd like Alex to do now, what note was that? All right, that is called an E note. We'll see them on the keyboard here in a second. But I'd like Alex to put his finger on the halfway point on that same string. Do you know where that is? Yes, it's right there. It's the 12th fret, so music people just happen to know, like they've memorized it's the 12th fret. And even for beginners, I think they put dots on that particular one because that's an important one. 2 dots go on that one. So again, play the open one. Is that, yeah, so open and then, yes. Okay, that is the same string plucked at the middle point, the halfway point. And what we just found out here is that those two things are called an octave apart, okay? And some of you guys are going to be able to hear this, and I apologize to those of you who just cannot hear the sameness of that note. It's just something that some of us cannot hear. but I'm hoping a bunch of us can hear. There's a quality about those two notes that is very, very similar. Can you play them again, Alex? So can you guys hear? Like it's the same kind of note as opposed to play the open one and then play like the 13th fret or something. Okay, those ones are really different notes. At least like I have some internal mechanism that's telling me those are different creatures. Play those two again. Can you guys hear that there's a differenceness there? But now play the octave ones. Same note, just higher pitch. That's all. Okay, and it happens at the halfway point. Johannes, you can keep going. Okay, so here are the notes in a full 12-tone scale. It starts with a C note. Anybody know what the number sign means? That's a sharp. Again, you don't need to memorize it if you're not a musician. That's okay. But anyway, C, C sharp, D, D sharp, etc. You can keep reading. Eventually, we loop back around to A, and then finally come back to C. Here's what it looks like on the piano keyboard, starting with a C. For example, the C right there in the middle. That note is the first note. That's the C. You come up here to this black key. That's a C sharp, also known as a D. And what's the B? B flat. All right, so that's the initial note. First note, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, and then the very next one over here, whoopsies. Oh, the very next one over there would be the C, and that would be the completing the 12-tone, 12-note scale. Now it's really confusing because we call each of those steps a half step. If it were me, I would call them steps, but we call them half steps. Every time you move to the right, it's a half step. Doesn't matter whether the key is black or white. Every note is a half step, okay? All right, so let's go down here. Now, unfortunately, I missed the spacing here and gave you guys something there's no way to read. So somebody with good eyesight, where's our reader now? Jason, can you read from the board, number 8?
There are many other possible scales. 12-tone scale, aka chromatic scale, was popularized by Bach.
Diatonic?
Diatonic scale, the 7 white keys on piano. Blues and jazz musicians use in-between notes. Composer Harry Arch made custom musical instruments to play compositions that employed a 43-note scale system. Non-Western music also uses a variety of scales. Okay, so we are going to focus on the 12-tone scale that is familiar to us here in the States. Piano, guitar, lots of things are based on that same thing, but there are instruments that we really don't use at all here that they use in other countries that just have a very different sound. So if somebody plays some music for me that was that originated in India, say, I might be able, I've never heard the song before, but I can at least identify, wow, that is very different from the Western kind of music that I'm used to. I'm not saying better or worse. I'm just saying this is not the only scale that's out there. It's the one we'll talk about because that's what we use here. All right, so let's go to number 9, which brings us back to population stuff. Okay, number 9. We'll go to Charlie.
Quick detour. Suppose the Earth population starts at 220 and the population doubles every 12 years.
Okay, can you guys, with your neighbors, do A, B, and C? We had a formula we saw today to answer this kind of question. Okay, so after 12 years, what happens to the Earth population? It doubles. So that one's easy because after 12 years, it would double from 220 to 440. But the other ones are not easy. The other ones we need a formula for because it's not a nice just doubling type thing. But we had our formula, and the formula said you take your starting population, 220 in this case, times it by 2 because it's a doubling thing. Up here is the elapsed time, down here is the doubling time. Elapsed time over doubling time. 1 year, 12 years. Any questions about typing that in and getting 220? Or 233, I mean? Okay. And then the same idea on the last one, but the elapsed time is now 28. And so we get a number much bigger, 1109. Okay? Okay. So we got those numbers, and now we're going to bring it back to the music. It feels like we're just kind of doing these like isolated, completely separate things. We've got population growth with doubling times, and then we've got music and frequencies and stuff. But we're going to bring them together right now. So take a look at this picture. Alex, can we grab that guitar again? So Alex is going to play for us the middle A. Do you know which one that is? Middle A. It might just be the open A string. I don't know. Is that a middle A? Where's middle C? Open set. Yeah, just play the open second string. Play the open fifth string. Top second from the top. Yeah, that way. Yeah, low A. Okay, I think that's middle. Is that middle A? It's the second one from the top. Okay, so the low A, but we call that middle A, and that has a frequency of 220. Anybody know the physics thing? Hertz. That means 220 up downs every second. That's why it looks like that big thick string. When Alex plucks that string, it vibrates at 220 oscillations every second. Can you play the halfway point on that string, which will give us the next octave? Everybody here, the first one was an A, the second one is the same thing. On the piano, you can see the first A is a 220, second A is a 440. What does it look like happens to that frequency when you go up the full octave? It doubles. Frequency goes from 220 at the low one to 440 at the higher one. Every time you go up an octave, you double. How many notes are there going up an octave? There are 12. There are 12 notes that you have to pass through to go up an octave. And every time I go up an octave, I need to double. Okay, now we're going to stop thinking of 220 as being a frequency. I'm going to think of it as a population. I've got 220 people. And instead of thinking it takes me 12 notes to double, what am I thinking? 12 years to double. And all of a sudden, this question that you just answered about population is really answering questions about frequencies of these notes. So let's think about this down here. You guys found the population after 12 years. I'm going to reframe that question. You guys found the frequency after 12 notes. What's the frequency starting from here after 12 notes? Frequency is 440. That's what you guys found. Something we didn't know until this moment right here. Instead of the population after 1 year, this is the frequency after one note. One note above the starting 220. If we take a look at one note above the starting 220, here's my start. Is B the one note above? It's the black key is the one note above. You got to count the black keys and the white keys. So this guy right here, you guys just found out, has a frequency of 233 hertz. One note above the starting note. That's why it's a 1/12. Okay, so play for us again the open A or the low A, and then the B sharp. Okay, so the first one was vibrating at 220 times a second. Second one at 233 times a second, a little bit faster. Could you guys figure out what the next note is vibrating at? How many notes up do you have to go from A to B? Actually, I have to go up 2 notes. So we're doing our formula now, 220 times 2 to the, all right, what goes on the bottom for every one of these? It's the doubling time, which is 12 notes always. Doesn't matter where you start. The frequency doubles every 12 notes. And what am I putting up here? Is a 2. You're going 2 notes above. I'm figuring the B. Yeah, so 2 notes above. We had to go to the B flat, and then we went to the B. And how much is that? 247. 247 is the frequency of that note. You could play this game as long as you wanted. You could find the frequency of every note on the keyboard. You guys found a frequency that was really, really high. That was, what was it, 1107? 1109? What note, where is that note? How do I find the note that you guys found at 1109? It's how many notes up from this A? It's 28 notes up. You guys found the population after 28 years. That's the frequency of the 28th note. All right, starting with A, which we're calling 0. If you just start counting up notes, 1, 2, 3, 4, 5, you keep going, you'll eventually land on the 28th key. What's the frequency of that 28th key? It's 1109. That's what it is. What if I asked you guys to go, let's do this. Suppose I tell you that middle C has a frequency of 256. Just going to give you that as a starting number. And I want to find the frequency of something that is 8 notes above. Can you guys do that? Starting from a middle C, which is a 256, I want the frequency of the note that's 8 notes above. I'll vote for 406. We got to kind of feel our way to a formula, but don't worry, it's written on the next page. What do I start with? 256 times that same basic formula. 2. What goes up there? 8, because it's 8 notes up. Down here, 12. This is what we type in. What is it? It's around 406. Starting note, however many notes above goes right up there. Always divided by 12 because we use a 12-note scale. Okay, just as well, we could go down the scale. What if I said I wanted to go 3 notes below? Yeah, the formula works just as well. If you're going 3 notes below, instead of putting an 8 up here where we have an 8, we would put a 3, but to say below, you put -3. Right? Go to the right, you got bigger numbers. Go to the left, smaller negative numbers. So if you guys type in, and the calculator knows what this means, and maybe from 105 you know what this means too, but 2 to the -3/12 means something very particular. We're not going to get into it, but maybe you saw negative exponents last semester. Maybe you saw fraction exponents last semester. But formula works, calculator gives us a number. Will the answer be more or less than 256? It's less because we know we're going to the smaller frequencies down here. So if you carefully type in 256 times 2 to the -3/12, how much? 250. Okay, what if I said this? How about I'm going to start at this guy, and I want you to go 2 octaves and 7 half steps above. From 440, that's your starting frequency. I want to go 2 full octaves and 7 half steps above. See if you guys can talk to your neighbors and get me that frequency. Okay, so we're going to our same basic formula. What's the starting frequency here? 440. I always do that. Okay, starting frequency is 440 times, what's the number to put here? 2, always times 2. There's a fraction. What always goes on the bottom? 12. If we use one of those instruments in another country, maybe there's a 43 that goes down there. But here it's always 12 for us. What goes on top is really one of the few things you need to figure out. If you are going 2 octaves, how many notes is that? 24. But I'm saying go 2 octaves plus another 7. So that's 31 half steps, 31 notes. 31 goes right up there. You should be able to ballpark this without the calculator. I can't tell you what 2 to the 31 over 12 is. I have no idea. But we could ballpark it because going up 2 octaves means you are doubling twice. So if you take your 440 and you double it, what do you get? 880. Then you take your 880 and you double it again, 1760. That's 2 octaves up. Then I'm going another 7 half steps. I don't know, 2,000, something, 2,500, something more than 1760. Not quite 3,400. What did we get when we typed it in? Questions on that? Okay, so we've been kind of playing around, and we didn't actually have the formula written out, so let's show you that there is a formula right here that we've been using over and over again. It's on the next page. It says if you want to find the frequency of any note, you put your starting frequency times 2, always, because we're talking about a doubling, to the number of half steps over 12, always, because we use 12-tone scales here. Questions on how to use the formula? Okay, so while we've got Alex and his guitar here, let's just talk a little bit more about the guitar as an instrument. Alex, could you come up here for a second? So if you're not familiar with the guitar and the frets, the little spaces on this long thing here, you can hold it. Are the spaces consistent? Like, can you guys see like the? Yeah, you can get out of the light. So the spaces, are they consistently spaced all the way top to bottom? What do you see on the top? What kind of spacing? There's bigger spacing on the top, and then progressively smaller spacing as we get down here, right? Okay, so there's a really, really good reason, and again, this was not just a random person deciding, oh, I want big spaces on top and small ones on the bottom, because aesthetically, I think that looks best. There's a math reason going on here. What did we decide was happening here at the halfway point? What happens to the frequency? It doubles the frequency, right? If you play an open one for us, and then play the halfway point. And I don't know if you guys noticed, but I mean, like literally, Alex's finger right here is at the halfway point between the top of the string and the bottom of the string. That's the one that gives you the next octave. I don't know if you can find it, but it's probably going to be hard to play, but put your finger there again. Okay, and then if there were a place halfway here again, now we're not going to be able to hear it because there's no board for me to put my finger on, but what would I find? I'd find another octave. Yeah. So is that the? It's hard to find it down there because there's nothing to push on. So that's about halfway. Can you play the regular, and then the next halfway, and then one more halfway maybe? It's close. It's around there somewhere. But if you keep going halfways and you're able to play them, you'll keep getting octaves up. Okay, so here's what's going on. We know that if we want to double the frequency, we need to cut the length of the string in half. So we got to somehow put, where's the middle one again? Okay, so on this line right here, we know that we've got the halfway point, which is the next octave. How many spaces are there above my finger? There's 12. They're counting the open note, because there are 12 notes, right? It's not just a random collection of spaces up there. I know that I need to get to the next octave when I put my finger on this halfway point. And I know there are 12 notes in an octave. So we got to fit 12 spaces up there above this halfway point. And we also have to decide how we're going to do it. Suppose that we measure this thing right here, and we decide that the length of this thing, I don't know, 30 inches. I don't know what it is. Let's just call it 30 inches, the length of the string. If I want to get to the next octave, how long is this supposed to be? 15. Okay, that's easy. What's not so easy is how long the next one is going to be. Like, is it 16 inches? Is it 15.8? I know the whole thing is 30. You know, is it 29 up here at the top? Is it 28? Let's see if we can figure out how to find that number. Okay, this is going to be a little bit of a stretch, not going to be on the test. But if I do over here 2 to the 1/12, which is our magical every step up, we've been doing 2 to the 1/12. So we never typed that number. We've never seen that number. We haven't seen it today. But every step to the right, every time you go up a note, we're multiplying by that number right there. So if we started at 220, and I'll just clear that right there, and I multiply that by the answer, I get the familiar 233. We got this number, right? You saw this number before. Of course you did, because you did 220 times 2 to the 1/12. That's what you did. Now, what you could do to get the next number is you could say, okay, if I'm already on 233, I could go up one note more from that, which is just another 2 to the 1/12. And we'll get another number we've seen. You guys saw that number. How many notes up was that from the starting A? That's 2 notes up, right? You saw that 247 today by going 2 notes up from the 220. But instead, you could just keep multiplying by 2 to the 112th. And in fact, if I hit it with another 2 to the 112th, that's the next note. And I could keep doing this. And I could find all the different notes that I wanted to. And eventually, actually, what's the next nice number I'm going to see? 440 will appear here in this sea of terrible looking numbers. Of course, it's double. It's the only one that's perfect. And if I keep going, what's the next nice one that we'll see? 880. We got lots of messy numbers and then magic. Okay, so that 2 to the 112th is somehow an important thing. 2 to the 112th is how much you have to multiply by to get to the next note. 1.059. All right, so what that means, frequency goes up by 1.059 every time you step to the right on the note, every time you step down on the fretboard. If I'm multiplying by 1.059 for the frequency, turns out I need to divide by it to get, let me call that number, I'm going to store that guy as X for a second. So that's just calling it X. If you multiply by X, you will get the frequency of the next note. What I'm trying to do is divide by X to find out how long I need to make this thing. Turns out that if the whole string is 30 inches, then the very next note, I need to put my finger at 28.3 inches, right here near the top of the 30 inches. So my finger is now pressing at 28.3 from the bottom. If I divide by another magical 1.059, I will find that the next note is supposed to be, oopsies. Oh, I should not have done that. Sorry about that. Yes, I should have done, okay, so we did 30 divided by X. We got that, and then I should have taken that and divided it by X. And I should find out that my next note should be at 26.7.
Does it get smaller as you go?
Let's see. So how much is the difference here? Whoever taught us how to subtract decimals is right now very, very sad. How much? 1.6-ish. Okay, so the first difference here is 1.6. How much was the difference from 30 to 28.3? That's 1.7. Next one is 1.6. Next one, how far apart are those numbers? 1.5. What you are finding here is the spacing of these frets. The first fret is going to be 1.7 inches. The next one is about 1.6. The next one is about 1.5. What's the difference here? Around 1.4. They're getting smaller. Not by a lot. You can't really see that the top few are much smaller than each other, but you can see the cumulative effect here. And if I keep dividing and I keep dividing, can you guys predict? There's actually going to be a nice number in this sea of bad ones. The first string was 30 inches long. We're going to get to 15 because we know that there's a magical halfway mark to the next octave. Okay, and how far apart are those two, for example? Only about 0.8, 0.9. So the difference down here, going from the, say, 12th fret to the 13th, is only 0.9 inches, whereas way up at the top was 1.7. And so there's this really, really nice sequence that you can find, the lengths of these frets. It's not arbitrary. They have to be put exactly where they've been put in order to get our notes to match up perfectly and get to the halfway mark at 15 inches, to get to that 12th note at 15 inches. Okay. All right, so what I'd like you guys to do is start. We'll give you lots of time today to do this math and music homework. So can you guys start with number 1 and work with your neighbors? The real important formula is the one right up above.